Okay. So I'm going to talk about improved upper and lower bounds for the VC dimension of piecewise linear neural networks. And this is joint work with Nick Harvey and Abbas Merabian. So we heard a lot about neural networks already, so I'm going to go through this slide really quickly. Mainly, we're just going to focus on the standard feed-forward neural network architecture. And for the nonlinearities here, we're just going to focus on the ReLU. So that's just the max of the input and zero. And at the output layer, we only care about, we're not going to have any nonlinearity there, so just put the identity there. And we're doing classification here, so we only care about the sign of the output. Okay, and just a quick reminder what VC dimension is. If you have a class of functions f, then its VC dimension is k if it can shatter a set of size k. And what shatter means is that it can shatter a set of size k if it can achieve all 2 to the k signings using functions from f. And as a quick example, hyperplanes in RD have VC dimension d plus 1. And the importance of this theorem, the classical importance of this theorem is the fundamental theorem of learning. And that says that the f is learnable if it has finite VC dimension, and actually its VC dimension determines its sample complexity. Okay, so one might ask, what's the VC dimension of neural networks? And so if you give me a neural network with W parameters and L layers, then there are some bounds known. So for example, Bartlett, Mayroff, and Mayer, they show an upper bound of WL log W plus WL squared. And interestingly, Goldberg and Jerem give another bound that's independent of the number of layers, and they show that it's upper bounded by W squared. But these upper bounds actually hold for the general polynomial networks for which ReLU is a special case. And there's also known lower bounds. So Bartlett, Mayroff, and Mayer, they show a WL lower bound. So there's actually a neural network with W parameters and L layers with a VC dimension at least WL. And similarly, Wolfgang Maass showed a lower bound that's independent of the number of layers. He showed a lower bound of WL log W. So one might ask, if we restrict to the ReLU case, whether or not we can get improved upper and lower bounds, especially if we can improve the dependence, or if we can tighten the dependence on the depth. And such a result is true. So our main result is that for a ReLU neural network with W parameters and L layers, the VC dimension is exactly WL up to some small log factors. Okay, and actually the upper bound was also independently proved by Peter Bartlett, but it hasn't been published yet. And there's also a lot of recent work on understanding depth on how it affects neural networks. For example, we saw a couple of talks earlier this session, and there's been a lot of work over the past year or so. Okay, let me talk about the lower bound. And our lower bound is based on a technique due to Bartlett, Mayroff, and Mayer. So we're going to try to share this set S. And S here is the set of basis unit vectors in Rn cross a set of basis unit vectors in Rm. So if I give you a function f, you should be able to set the weights of the neural network in such a way that given input ei, ej, the output of the neural network is exactly f of ei, ej. So one idea to encode this is to store f inside the weights of the neural network itself. So for example, you can have a weight ai where the jth bit of ai is exactly f of ei, ej. And so one neural network architecture that was considered by Bartlett, Mayroff, and Mayer is something like this. And here, this red part, the output of this red part here, exactly AI. And so if you're given input EI, EJ, to get the answer, you just need to extract the jth bit from AI. And so this leads to a natural question of how you can use a neural network to do bit extraction. And I claim that if you were able to extract all the bits, then designing the rest of the network is actually very easy. So really it just comes down to designing this bit extraction block. And there's various ways you can think about doing it. In the Bartlett paper, they show that you can do this by extracting a single bit every 1 or 2 layers. And this leads to a lower bound of WL. But actually you can do something a bit more fancy. And in our paper, we were able to find a way to extract log W over L bits per layer, and that leads to a lower bound of WL log W over L. And I don't have time to go over this construction. And interesting enough, you can't actually push this technique any further. So if you try to do bit extraction, then you hit this barrier where, any ReLU network with W parameters and L layers, if it extracts the nth bit, then that bit position can't be too far away, so it has to be at most L log W over L. And so, using this bit extraction idea, the best lower bound you can hope for is exactly this quantity. Okay, and let me also talk a bit about the upper bound. And again, this is refining some ideas from Bartlett, Mayroff, and Mayer. So the idea of the upper bound is, well, first let's suppose that the neural network shatters a set X of size M. Then trivially, it must have 2 to the M signings. And now we're just going to count the number of signings in a different way, but this time based on some of the parameters of the neural network. And the idea is that if we can somehow remove these nonlinearities and make them trivial, say either 0 or the identity, then this just becomes the output of the neural network just becomes a polynomial in terms of the weights of the neural net. So we're going to start off by partitioning the parameter space so that the input into the first layer all have constant sign. And if we do something like that, then these nonlinearities are really just trivialities. They're either the identity or the 0. The identity if the input is positive, and they're 0, the input is negative. And so the output of that is just a polynomial, and the partition actually ends up being quite small. So if you dig into the literature and look at algebraic geometry, you'll find a theorem due to Warren which talks about the number of signings that a polynomial or a vector of polynomials can have. And then you apply that theorem here, it turns out that the size of the partition into this first layer ends up being only about Cm to the W for some constant C. And then you can repeat this process for each layer, and the number of signings that you get, or the size of the partition that you get is this quantity, and it turns out that the number of signings is also has a similar expression, just the constant in the exponent changes. And because this is an upper bound in the number of signings, and 2 to the m is the exact number of signings, you can then solve the equation to get an upper bound of WL log W. Okay, let me just end with some open questions. So there's a really annoying gap in our there's a really annoying gap in the theorem. So there's a lower bound of WL log W over L and an upper bound of WL log W. It'd be nice to try to figure out which one of these are the correct answers. And for polynomial neural networks, the best known lower bound is only WL, and the best known upper bound is WL squared. And it'd be interesting to see if we can try to tighten this gap. And at the very least, we would like to know if the lower bound, the dependence on depth, can be increased to say L to the 1.0001. And there's also a lot of other architectures that are used in practice. For example, convolutional neural nets, recurrent neural nets, or residual nets. And it'd be interesting to study the VC dimension of those networks. And that's all I have to say. Thanks.
Mm-hmm. You calculate the dependence on the number of linear pieces?
So the pieces are constant. I believe it's a logarithmic dependence on the number of pieces.
And that's tight on both sides?
That's tight on both sides. Well, it's tight on one side. I'm not sure. I'm actually not sure about the other side. So that's an interesting question.